Okay, in this video I'm going to talk about sequences. A sequence is a rule that assigns a real number to each natural number. So natural numbers being whole counting numbers, like numbers that you can count to on your fingers, 1, 2, 3, 4, 5, and so on. And so we denote a sequence a sub n, we call it a sub n, from n equals 1 to infinity in this way here. And so the rule we typically write as the nth term. So this would be the nth term here. A sub n is equal to 1 over n. So this gives us enough information to talk about our entire sequence, right? Because a sub 1 will be 1 over 1, which is 1. A sub 2 will be 1 over 2, so 1/2. A sub 3 will be 1 over 3, 1/3, and so on in this way. And we can denote the entire sequence an from n equals 1 to infinity equals 1 over n from n equals 1 to infinity, which is equal to 1, 1/2, 1/3, 1/4, and so on in that manner. Okay, so let's give the general term of the following sequences. So we just need to look at the sequence and figure out what the pattern is going on here. So the first thing I notice, so maybe I'll label my points A1, A2, A3, A4. Okay, and the first thing I notice is in the numerators, it's just increasing with the number of the term. So I'll have n over something. So my an is going to be n over something. So for these bottom terms, let's kind of look, one strategy is to try and rewrite these terms as something else. So I can rewrite 2 as 1 plus 1. I can rewrite 5 as 4 plus 1. I can rewrite 10 as 9 plus 1. I can rewrite 17 as 16 plus 1. And I start to see a pattern here. These are just the squares of the numbers that, the square of the number of the term. So my denominator here will have the form n squared plus 1. Okay? And I already knew the answer, so I made it look very easy, but I know in general finding the rules for these isn't very easy. It takes a lot of trial and error. So one of the strategies is to kind of rewrite your terms to figure out, or to rewrite numbers to figure out if you can see a pattern in that way. The next sequence we'll look at is -1, 2, 7, 14, 23. So let's try rewriting again. So -1 is the same as 1 minus 2. Let's try 2 is the same as 4 minus 2. 7 is the same as 9 minus 2. 14 is the same as 16 minus 2. And so on, right? So this means my sequence, I noticed that these are just the n squareds, right? So this is 1 squared, 2 squared, 3 squared, and so on. It's going to be n squared minus 2. So that is my sequence. That's the nth term of my sequence. Okay, and this next one's a little bit more tricky. The first thing I want to do is I want to rewrite 2 as 2 over 1, because everything else is in a fraction, so why shouldn't 2 be? And this should give us an idea. In the denominators, I notice that everything is odd, okay? So I have 1, 3, 5, 7, 9. Those are the odd numbers. And we can write odd numbers as either 2n plus 1 or 2n minus 1, right? Because if n is 1, this gives me 3. This gives me, if n is 0, it gives me 1. If n is 1, it gives me 3. If n is 2, it gives me 5, and so on. For this one, starting at 1, if n is 1, this gives me 1. If n is 2, this gives me 3. If n is 3, this gives me 5, and so on. So I want to use 2n minus 1. So my denominators will be 2n minus 1. Okay? The top, I have 2, 4, 8, 16, 32. Well, what I see here is 2 to the 1, 2 squared, 2 cubed, 2 to the 4th, 2 to the 5th. So it's 2 to the n over 2n minus 1. That would be my nth term. Okay? So, in general, finding these rules isn't super important. Typically, you'll just be given the nth term, and you could write out terms in the sequence if you wanted to. But it's good to know how to kind of get the nth term off of just a list of ordered numbers. Okay? And we say a sequence is increasing if the nth term is smaller than the n plus 1th term. Okay, so this is saying that if I have, for example, let's say n is equal to n, right? Then this is strictly increasing. It's obvious that this will be from n equals 1 to infinity will be 1, 2, 3, and so on in that order. And for any n, I have that n is less than or equal to, well, strictly less than n plus 1. So this is an increasing sequence, okay? And I kind of spoiled it, but we say that it's strictly increasing if an is strictly less than an plus 1. So each term is smaller than the next, and that's pretty intuitive for what it means to be increasing. Another way to restate this is to say that, so I can take this inequality here and divide both sides by, I can take this inequality here and divide both sides by an plus 1. So if an over an plus 1 is less than or equal to 1, it's also increasing. Okay, same idea. We say it's decreasing if the opposite is true, right? If an is greater than or equal to an plus 1, so each term is greater than the next, or the next term is less than the first. So, for example, minus n would be a good example of this. So an equals minus n, so minus 1, minus 2, minus 3, and so on. Each term is bigger than the next, so this is decreasing. Again, we say it's strictly decreasing if an is greater than an plus 1, strictly greater than. And similarly, we can rewrite this as an over an plus 1 greater than or equal to 1. Okay. We say it's bounded above if there's a number capital M such that an is less than or equal to m for all n. So that says that every term in the sequence is smaller than some number. And the smallest upper bound, so the smallest number that bounds the sequence above, is called the least upper bound. We say that the sequence is bounded below if there's a lowercase m such that an is greater than m for all n. So this means that there's a number such that every term in the sequence is greater than that number. And we say that it's bounded below by that number. The biggest lower bound is called the greatest lower bound. Okay? So the biggest of these lower bounds is the greatest upper bound, and the smallest of the upper bounds is the least upper bound. Okay? We say it's monotonic if it's either increasing or decreasing for all n, so it has to be strictly, well, one way or the other, right? It can't increase, then decrease, then increase, then decrease. You might think back to monotonicity from Cal 1, right? So if it's strictly increasing, or it's, only decreasing, then it's monotonic. And we say it's convergent if there's a number L such that a sub n goes to L as n goes to infinity. So this is very much our idea of limits at infinity from Calculus 1. The limit as x goes to infinity of f of x is just kind of like a horizontal asymptote. This is kind of our idea for sequences, is that sequences can approach a number very closely, and we'll kind of get an idea of that with these examples below here. So we're going to take these kind of terms here, and we're going to classify these example sequences in terms of these terms, okay? So the first sequence we're going to look at is 4 minus 1 over n from n equals 1 to infinity. Okay, so first I think I'll start with figuring out if this is a convergent sequence, right? If there's a limit such that as n goes to infinity, this goes to a number. So we'll literally just take the limit in a Cal 1 sense, the limit as n goes to infinity of 4 minus 1 over n. Well, limit as n goes to infinity of 1 over n is 0, so this is going to be just 4. So it converges to 4. Great. Okay, next we're going to check if it is monotone, right? If it's increasing or if it's decreasing. So we want to figure out the relation between an plus 1 and an. Okay, and one way we can do that, and one way I like to do that, is by just putting an r between them. Because you and I know how order relations on numbers work, right? Greater than, less than, greater than, equal to, less than or equal to. The relationships only change when we multiply or divide by a negative number, right? So if we assign a dummy relation, say r, kind of like a variable, and if we multiply or divide by a negative, we just flip r, then we can kind of reduce things down to something that we know, and we can say what r must have been all along. So let me just give the example here. So an plus 1 in this case is going to be 4 minus 1 over n plus 1, and that is going to be related to, in some way, 4 minus 1 over n, okay? Well, I notice that I got a 4 on both sides, so I can cancel that without doing anything. And I'm left with negative 1 over n plus 1 r negative 1 over n. I can multiply both sides by negative 1, and I can get that 1 over n plus 1. I'm going to put the r backwards now. It's not the best way, but r. This is not going to look great, but 1 over n plus 1 is backwards related to 1 over n. And we know that 1 over something larger is smaller. So this tells me that this backwards r is the less than relation, okay? Because we know how these are related for certain. So if I flipped it here, this must have been greater than. This must have been greater than. And so originally, an plus 1 must have been strictly greater than an, okay? So using this placeholder r allows us to determine what the order relation between an plus 1 and an was. And so what we can conclude from this is that the sequence an is increasing, right? Because an plus 1 is strictly greater than an. Increasing. Strictly. And because of that, it's monotone. So it's monotone increasing. Monotone. Okay, great. The next thing we want to figure out is least upper bound, greatest lower bound. So my least upper bound is going to be the smallest upper bound. So if it's increasing and it's, we're talking about, so if I was to like graph this, for example, my sequence is increasing. So it's increasing, 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 but it also converges. So it must be getting closer and closer and closer and closer to 4. So if I'm getting closer and closer and closer to 4, my smallest term must have been my first term. And my largest, the largest the sequence can possibly get, it never quite gets there, but it gets arbitrarily close, is 4. So immediately I can read off that my least upper bound must have been 4. And my greatest lower bound must have been the first term in the sequence, so a1, which in this case is 4 minus 1, so 3. So my least upper bound is 4, and my greatest lower bound is 3. Great. Okay, moving on. We have n squared over 2n from n equals 1 to infinity. The first thing I want to do is determine if this has a limit. So limit as n goes to infinity of n squared over 2 to the n. It should be pretty clear that this is 0, because this 2 to the n grows much, much faster. Grows much faster than n squared. So we can definitely say that that goes to 0. So this is convergent. So this converges to 0. The next thing we need to do is figure out how the terms are related. So again, I'll use my trick of the placeholder r. So an plus 1 r an, so it's related in some way to an. Let's go ahead and plug in definitions here. So n plus 1 squared over 2 to the n plus 1 is somehow related to n squared over 2 to the n. Okay, what I can do is I can, in a sense, what I'll do is I'll multiply both sides by 2 to the n and 2 to the n plus. Or actually, I think what I'll do here is I will, I'll multiply both sides by 2 to the n and 2 to the n plus 1. And because those are both positive, it doesn't change the order of my relation. So r stays the same. So I have 2 to the n plus 1 squared times 2 to the n plus 1 times n squared. I'll go ahead and divide by 2 to the n plus 1 and n plus 1 squared. Again, not dividing by anything negative. So my r stays the same. So I have 2 to the n over 2 to the n plus 1, n squared over n plus 1 squared. Okay, this gives me 1/2 is related to n squared over 2n plus, n plus 1 squared. And then, so maybe it might be better to reciprocate things to get a better idea of what's going on. So let's see. I will multiply both sides by n squared plus 1, or sorry, n plus 1 squared, and then divide by n squared, and I'll multiply both sides by 2 to give me this. And so let's just take a look at some of the values to determine when this actually happens, because from here we should be able to kind of get when this, well, maybe, you know what, let's do this. Let's expand this n plus 1 squared. So I have n squared plus 2n plus 1 over n squared. It's related to 2 in some way. And I can go ahead and write this as 1 plus, 1 plus 2 over n plus 1 over n squared related to 2. Okay. Now, let's look at this. So if n is 1, so for n equals 1, this is 1 plus 2 plus 1. Clearly that's greater than 2. But if n is, let's say, maybe 4, let's say 4, then this is 1 plus 2 over 4 plus 1 over 16. Well, that's 1 plus a half plus a 16th. And it should be clear that this is less than 2, because a 16th is less than a half. This is actually less than 2. So this relation depends. So it depends on n. So it's not strictly increasing or decreasing. We can't say anything about the relation between the nth term and the n plus 1th term unless we know what n and n plus 1 are. And so we can't say that this is strictly increasing or decreasing. Okay. So next, let's see if we can find a least upper bound or greatest lower bound. So the way I'll do this is I will appeal to calculus. We know that a function, so this n squared over 2n, it kind of it's interpolated by the smooth function x squared over 2 to the x. So we can use information about the smooth function x squared over 2 to the x to determine when this sequence is going to have a minimum or a maximum. Okay, so let's take a look at this. Let's think about, from calculus 1, we know that when the derivative is 0, there is a minimum or a maximum. So I'll take the derivative of this, replacing n's with x's. Take the derivative of this to give me, it's going to be 2x times 2 to the x minus, right by quotient rule, minus x squared ln 2 to the x over 2 to the x squared, which is 2 to the 2x. Okay, so, and I want to set this equal to 0 to find minimums and maximums of my original function. So what I can do here is I can go ahead and cross this, and this out. So I'm just left with all of this over 2 to the x. And then I care when it's 0, so I only care when the numerator is equal to 0. So that's when 2x minus x squared ln 2 equals 0. I can factor this and get that x times 2 minus x ln 2 equals 0. So my options are when x equals 0 or when 2 minus x ln 2 equals 0. That's when x equals 2 over ln 2. Okay, and this 2 over ln 2, this is between, because ln 2 is slightly less than 1. So this is going to be between 2 and 3. Okay. And so I have to pick, I'll look at, because this is near n equals 1, so I'll test n equals 1, 2, and 3 to see which of them is the greatest and which of them is the least. Okay, and that'll help me determine what my least upper bound and my greatest lower bound are. And I also know that my function converges to 0, so that's a potential for the least, or greatest lower bound or least upper bound. So let's evaluate a1 here is equal to 1 squared over 2 to the 1, which is 1/2. A2 is equal to 2 squared over 2 squared. That's just 1. And a3 is equal to 3 squared over 2 to the 3, which is 9 over 8. Okay, so clearly 9 over 8 is larger than 1, so this is going to be my least upper bound, because it's the value that the function actually takes. And then my greatest lower bound, my candidate was a equals 1, but really 0, because it eventually gets arbitrarily close to 0, is going to be my greatest lower bound. So 0 is my greatest lower bound. Okay. And then moving on, let's take a look at the sequence n over ln n. So again, let's see if this has a limit. First thing, let's see if this has a limit. So the limit as n goes to infinity of n over ln of n. Well, clearly this is going to go to infinity because n grows much faster than ln n. So this is going to go to infinity. And so now let's take a look if there's a relation between an plus 1 and an. So I'm going to use my trick again. So I have n plus 1 over ln. N plus 1 is related in some way to ln over ln n. Okay, so maybe we just test some values here and kind of figure out how things are related. So maybe we, let's go ahead and multiply both sides by ln n and ln n plus 1 to give us ln n times n plus 1 times ln n plus 1 times n. And then I want to rewrite this using log rules as ln of n to the n plus 1 is related in some way to ln n plus 1 to the n. Okay, and then I can exponentiate both sides, and that preserves log rules, or that preserves the relation rules. So this tells me that n to the n plus 1 is related in some way to n plus 1 to the n. So it's not clear how these are related, but it might be a little bit more clear if we plug some values in. So if n is 1, this is 1 squared, and it's related in some way to 2 to the 1. So clearly 1 is less than 2. If I plug in 2, this is 2 cubed, and this is going to be 3 squared. 2 cubed is 8, and 3 squared is 9. Okay, good. It's looking good so far. What happens if I plug in 3? Well, I have 3 to the n plus 1, so 3 to the 4. And then I have, it's related to, we're hoping that it's less than, right? So we're hoping that this is consistent. 4 to the 3. Well, 3 to the 4 is 81. And we're hoping that that's less than 64, and it's not. So this relation depends. It depends on n, so it's neither increasing nor decreasing. It changes depending on what n is. Okay, so again, let's get an idea of if we can have a greatest lower bound and least upper bound. So I'm going to do the same trick I did before and look at the continuous function x over ln x. The derivative of that, when I set it equal to 0, will give me the minimums and maximums. So let's take the derivative. I get ln x minus x times 1 over x over ln squared x. And I want to set that equal to 0, so I only care when ln x minus 1 equals 0. So when ln x equals 1, or when x equals e. So I exponentiated both sides. And we know that e is between 2 and 3. So I'll test a2 and a3 to see if which one of those is greater, or determine if I have a least upper bound or greatest lower bound. Let's see here. So n over ln n, it should be pretty clear that it's after a certain point increases, right? So for very large n grows much faster than ln n, so overall this is going to be increasing. It's just these terms down here that kind of mess things up. So it's not increasing forever, but after a certain point it does continue to increase. And so we should have that, let's see. We should have a greatest lower bound but no least upper bound because it goes to positive infinity. So my lowest upper bound doesn't exist. So we're looking for a greatest lower bound. Okay. And so let's check those values here. So we're looking for the largest one. A2 is 2 over ln 2, and A3 is 3 over ln 3. Okay, let's use our trick to see how these are actually related to one another, because it doesn't appear to be very obvious. So 2 over ln 2 are 3 over ln 3. Multiply both sides by those ln's, and I get ln 3 are, so 2 ln 3 is 3 ln 2. And this tells me by log rules that I'm going to have 3 squared is related to 2 cubed. And 9 is strictly greater than 8, so this relation must have been greater than all the way up. And so I must have had that A2 is greater than A3, so A2 must have been my greatest lower bound. Okay, and that wraps up my examples. If you found this video helpful, please consider liking and subscribing. Thanks.